In a previous lecture, you saw an example of definite integration with u-substitution, and now in this lecture we're just going to focus on a number of examples using that technique exclusively. And this technique is ultimately used to undo the chain rule. So let's consider our first example, the integral from 0 to 2 of x times x squared plus 1 squared dx. Now in this case we do have the option of simply multiplying everything out and integrating that way. We don't have to. We can use u-substitution. In this case I'm going to let u equal x squared plus 1. And this means that du equals 2x dx. And since what I have is x dx, if I divide both sides by 2, 1/2 du equals x dx. So now I have everything I need to substitute. So my initial integral will become, since u is x squared plus 1, u squared, and x dx is equal to 1/2 du, so I'll have 1/2 du. The only issue that remains is changing my limits of integration so that they're in terms of u. And I'll use my relationship, what u equals in terms of x, to do that. So let's start with the upper limit of integration. It's currently 2, and it's in terms of x. What does u equal when x is 2? Well, u equals 5. And when I check my lower limit of integration, in this case 0, what does u equal when x is 0? u equals 1. So in terms of u, I'm integrating from 1 to 5. What's nice about this, though, is I don't have to go back in order to evaluate this. I know that the integral of 1/2 u squared will be, what's that going to be? U cubed. So 1/6 u cubed. And I'm going to leave my limits of integration in terms of u from 1 to 5. Now I can evaluate it just like this. If I leave it, 5 cubed is 125, so 125 over 6 minus, I'm going to substitute in 1 over 6, and this becomes 124 over 6, which is equivalent to, let's see, everything's divisible by 2, so 62 over 3. And just so you can see that it ends up being the same, in case you're concerned, if I change everything back to x, this will end up being 1/6. u was x squared plus 1, and x squared plus 1 cubed. And in terms of x, my limits of integration are from 0 to 2. If I substitute in 2, 2 squared is 4, 4 plus 1 is 5, 5 cubed is 125 over 6. If I substitute in 0, 0 plus 1 is 1, 1 cubed is 1, minus 1/6, and we already know that will equal 62/3. So we can, once we change it in terms of u to evaluate a definite integral, we can just keep working with everything in terms of u. Let's consider a number of other examples. Here we have the integral from 0 to 1 of x times the square root of 1 minus x squared dx. I'll let u equal 1 minus x squared. So du equals negative 2x dx. I need x dx, so if I multiply both sides by negative 1/2, I've solved for x dx, and I'm ready for u-substitution. This will become u to the 1/2 and times negative 1/2. My upper limit of integration, well, when x is 1, u is 0, and my lower limit of integration, when x is 0, u is 1. So I'll just be evaluating it. in this way. U to the 1/2 goes to u to the 3/2, and multiplying by 2/3, this will be, must have been negative 1/3 to begin with. I'm evaluating it from 1 to 0, so substituting in 0, this will be 0 minus, substituting in 1, we'll get negative 1/3, and so altogether the value of the integral is positive 1/3. We'll consider some more examples. Here we have the integral from 0 to root 5 of x over the square root of x squared plus 4. I'll solve this by u substitution. If u equals x squared plus 4, then du equals 2x dx, which means that 1/2 du equals what I need, x dx. So, by substitution, this will become, since u equals x squared plus 4, it will be u to the negative 1/2, and x dx is equal to 1/2 du, so 1/2 du. My limits of integration will change. When x is 0, u would be 4, again just using this equation, and when x is root 5, u would be 9, so I'm integrating from 4 to 9. When I integrate this, this goes to u to the 1/2 from 4 to 9. The square root of 9 is 3, the square root of 4 is 2, 3 minus 2 is 1. Let's consider another example. The integral of sine 2x. So I'm integrating from 0 to pi fourths of the sine of 2x dx. I will let u equal 2x. This means that du equals 2 dx, or 1/2 du equals dx. Now I'm ready to substitute. So this will become the integral of 1/2 sine u du. And if I change my limits of integration, when x is pi fourths, my upper limit will become pi halves. Again, just using u equals 2x to make the change. And my lower limit is 0, so u would be 0 in that case. The integral of 1/2 sine u is negative 1/2 cosine u. That's going to be from 0 to pi halves. The cosine of pi halves is 0, so this will be 0 minus, the cosine of 0 is 1, and 1 times negative 1/2 is negative 1/2. So the overall value of this will be positive 1/2. We'll consider 3 more. In this problem, we're integrating sine x times the square root of cosine x dx. I will let u equal cosine x, which means that du equals negative sine x dx, which means that negative du equals what I need, sine x dx. So I'm ready to substitute. This will become negative 1 times u to the 1/2 du. And my limits of integration will change from, let's see, the cosine of 0 is 1, and the cosine of pi halves is 0. Integrating, u to the 1/2 becomes u to the 3/2. This must have been, this is already negative 2/3 to begin with, and I'll be integrating from 1 to 0. Substituting in 0, we'll have 0, minus substituting in 1, we'll get negative 2/3. And so altogether, this is equal to 2/3. There's two problems left for us to consider with u-substitution. The next one we'll do is the integral from 0 to pi sixth of 1 plus sine x cosine x dx. And to make it easier to see the u-substitution necessary, we've really got two integrals here, from 0 to pi sixth of 1 dx plus the integral from 0 to pi sixth of sine x cosine x dx. And this first integral is pretty easy to do. 1 dx is equal to x from 0 to pi sixth. When we evaluate this, this part's equal to just pi sixth. So it's pi sixth plus whatever this other integral is equal to. And so now we'll pay attention to sine x cosine x dx. This one I'll solve by u-substitution. If u equals sine x, then du equals cosine x dx. So this integral becomes the integral of u du. And if we change our limits of integration, pi sixth, well, the sine of pi sixth, let's see, pi sixth is equivalent to 30, so that'll be 1/2. And if we check our lower limit of integration, the sine of 0 is 0. Integrating u, this must be 1/2 u squared. That'll be from 0 to 1/2. If you substitute in 1/2, 1/2 squared is 1/4. 1/4 times 1/2 is 1/8, and this will be 1/8 minus 0, which is just an eighth. So this whole thing will become pi sixth plus 1/8 for a final answer. There's one problem left for us to do, and wouldn't you know it, it's an absolute value problem. We're looking from -2 to 2 of the absolute value of 1 minus x squared dx. So first let's consider the graph of this thing. Now I know that 1 minus x squared is a parabola that opens down, and it has intercepts at -1 and +1 respectively. But on the absolute value, this part that was down below would be positive, so it's doing something like this graphically. Right, so that's some very odd things to make sense of with this example. Now, one thing to notice is that this graph is symmetrical. That is, this side from 0 to 2 is equal to this side from -2 to 0. So I'm going to look at only half of this from 0 to 2, and I'll double my answer. So I'm going to look at 2 times the integral from 0 to 2 of the absolute value of 1 minus x squared dx. Now, the absolute value of 1 minus x squared is, in a sense, it's two functions. It's 1 minus x squared sometimes, and it's the opposite of that other times. Or it is x squared minus 1 at other times. And we just need to determine when we're dealing with each piece. Now, before 1, here, I should circle it in red, here is when we're dealing with the part of the parabola that's opening down, 1 minus x squared. And after 1, I'll circle it in blue, we're dealing with the part that's opening up, x squared minus 1. So that's our graphical clue with regards to what's happening. That means that our integral then is really two parts. So I'm doubling both of these integrals. the integral from 0 to 1 of 1 minus x squared dx plus the integral from 1 to 2 of x squared minus 1 dx. And you'll notice I'm not sure why I would consider using u-substitution here. In fact, I don't know that I'm going to. If I evaluate this, I know that 1 minus x squared becomes x minus 1/3 x cubed, and I'll be looking at that from 0 to 1, plus I know that x squared minus 1 becomes 1/3 x cubed minus x, and that'll be evaluated from 1 to 2. So now I just need to really use my grouping symbols to help me out. Dealing with this first integral from 1 to 0, when x is 1, I'll have 1 minus 1/3, or 2/3. That'll be 2/3 minus 0. Plus, now I'm dealing with the second integral. When x is 2, I'll have 8/3 minus 2, or 8/3 minus 6/3, which is just 2/3. And when x is 1, I'll have 1/3 minus 1, or 1/3 minus 3/3, which is negative 2/3, so minus negative 2/3. When I put all of that together, I've got 2/3 plus 2/3 plus 2/3, or 6/3, or just 2, and 2 times 2 is 4. So I didn't use u-substitution there, but I had to use some creativity to solve that problem. So there you have a number of examples of definite integration, mostly involving u-substitution.